Have you ever considered that? Time, something seemingly immutable, passing by steadily with each tick, could actually be bent, stretched, or even slowed down? You glance at the clock, feeling each second pass regularly, seemingly as a given. But what if I told you that time can be warped, elongated, or even decelerated depending on where you are in the universe? Would you believe it? Imagine you and your best friend amidst the vastness of space, traveling together on spaceships gliding close to the speed of light. Initially, everything proceeds as usual. Laughter and casual conversation still echo between the two ships. Time, like a gentle stream, flows familiarly. But then, your ship accelerates, approaching an unimaginable speed threshold. From your perspective, a strange phenomenon begins to occur. Your friend's ship, seemingly darting swiftly, appears to slow down gradually. Every movement they make, each wave of their hand, seems to slow down like a slow-motion film. Even the messages they send are stretched out, as if struggling to overcome a thickened flow of time. Yet, from within that ship, your friend is completely unaware. For them, time continues at its normal pace, and the ship still glides through space. So, what created this strange difference? Why is the same event observed in two completely opposite ways? The answer lies in the effects of relativity. When the speed approaches the speed of light, or when an object possesses a massive mass like a black hole bending space-time around it, time is no longer a constant. It begins to change, to warp, in ways beyond human imagination. Let's go back to the 17th century, when Isaac Newton, a genius of physics, was sitting pensively under a tree. According to legend, the moment an apple fell to the ground sparked a revolutionary idea in his mind: gravity, an invisible force pulling everything towards each other. But for Newton, that wasn't the end. He believed that time was also absolute, just like gravity. In his view, time flowed steadily and unchanged, regardless of weather. You were standing on the ground or drifting in space. This idea dominated for centuries, especially in explaining everyday phenomena. However, there was a big question Newton couldn't answer. How could massive objects like the Earth and the Moon affect each other from a distance? What he didn't realize was that time was not as simple or immutable as he thought. Nearly 2 centuries after Newton, another brilliant mind changed our understanding of the universe: Albert Einstein. He not only challenged Newton's idea of absolute time, but also introduced a completely new perspective. According to the theory of general relativity, Einstein proved that time is not a steady, immutable flow. Instead, it can contract, slow down, or speed up, depending on your speed or the gravitational force where you are. Imagine you are approaching a black hole where the gravitational force is so strong that time almost freezes compared to someone standing on Earth. Here, not only space but also time is bent, curved like a flexible fabric under the weight of massive objects. Einstein's theory shattered the long-held belief that time flows the same for everyone, showing that it changes depending on your position and movement in the universe. The flexibility of time does not exist only in the present. Going back to the moments after the Big Bang, the early universe, hot, dense, and filled with intense gravity, caused time to flow so slowly that it almost stopped compared to today. This is not because the clocks were wrong, but because the strange nature of the universe at that time stretched time. Time in Einstein's light is no longer a rigid entity. It is alive, changing, and contains mysteries that we have only just begun to reveal. A reality once considered absolute has now become a fascinating concept where space and time merge, together telling the great story of the universe. Einstein's theory of general relativity not only changed our understanding of time, but also painted a fascinating picture where time and space merge into a unified entity, the space-time fabric. In this fabric, time is no longer a linear, immutable flow. It becomes flexible, capable of being bent, stretched, or even twisted by gravity and motion. Imagine the universe in its early moments right after the Big Bang. All the massive mass and energy were concentrated in a tiny space where the density reached its extreme. The gravitational force here was so strong that not only was space compressed, but even time was stretched. 1 second in that chaotic state could be equivalent to millions of years, as we measure time today. This is the effect of gravitational time dilation, a strange phenomenon that occurs when time near objects with extremely high energy density flows slower than time far from them. Einstein described this with his great field equations, where gravity is no longer understood as a normal force, but as the curvature of space-time itself. When a massive object like a black hole appears, it strongly distorts the space-time fabric around it, creating a warped space-time region where time slows down, almost stopping. It is from these discoveries that Einstein not only opened the door to a deeper look into the nature of the universe, but also made us realize that time is not an immutable reality. It is part of a universe full of mystery and wonderful connections. Today, this effect still exists and can be clearly observed. On Earth, our planet's gravity causes time near the ground to flow slightly slower than at the altitude where satellites orbit. This difference is too small to notice in everyday life, but is extremely important for GPS technology. To ensure absolute accuracy in positioning, satellites must constantly adjust to compensate for the phase difference of time, a vivid demonstration of the impact of gravity on the flow of time. But this effect truly reveals its incredible power when we approach objects with extremely strong gravity, like black holes. At the edge of the event horizon, the boundary beyond which nothing can escape, not even light, time is stretched to a strange extent. To a distant observer, an object falling into a black hole appears to freeze right at the edge, as if time for it has stopped. This means that if you observe an object falling into a black hole, you will see it as if frozen at the edge of the event horizon, a vivid demonstration of the strange curvature of time. Time is not only distorted by gravity, but is also strongly influenced by speed. According to the theory of special relativity, when an object moves close to the speed of light, time for it seems to slow down compared to a stationary object. This is not just theoretical, but has been proven through experiments in modern particle accelerators. There, atomic particles accelerated close to the speed of light live significantly longer than when they are at rest, as if time for them is stretching out. This effect is not limited to laboratories. Imagine you are traveling through the universe at near light speed. When you return to Earth, you will be amazed to find that much less time has passed for you than for those who stayed home. This is the famous twin paradox that Einstein predicted, a powerful demonstration of the deep connection between speed and time. But to understand better, let's go back to the dawn of the universe. When the universe was small, hot, and densely packed with energy, all these factors, high energy density, intense gravity, and rapid expansion, combined, slowing down the flow of time to almost a standstill. Only when the universe expanded, cooled, and entered a more stable state did time gradually regain the familiar flow that we know today. According to Albert Einstein's theory of special relativity, time is no longer an immutable quantity, but instead depends on the velocity of an object relative to the observer. When an object moves at a velocity close to the speed of light, time in its reference frame seems to slow down compared to the reference frame of a stationary observer. This is the phenomenon of time dilation due to velocity, strong evidence that time is bent by both velocity and gravity. When the velocity of the object approaches the speed of light, time for it almost stops completely. This is the foundation of time, not being immutable, but being bent by velocity and gravity. When we observe light from distant galaxies, we are actually looking back billions of years to the very dawn of the universe. The light from these galaxies not only tells the story of the past, but also reveals that time has changed. In its journey across expanding space, light is stretched, creating a phenomenon called redshift. But it's not just light that is stretched. Time itself is also distorted in this process. Quasars, brilliant celestial objects belonging to the early universe, are a vivid example. When observed, they seem to move slower than quasars today. Not because their nature is different, but because the continuous expansion of the universe has stretched everything, from light to the rhythm of time. The light from these quasars has to travel a long journey to reach Earth. In the world of physics, time doesn't always flow steadily, and the way it operates can amaze you. A prominent example is the twin paradox. Imagine two twins starting from the same point. One decides to take a journey at near light speed, while the other stays on Earth. When the traveler returns, they find that they have aged very little, while the sibling on Earth has experienced decades. This phenomenon, explained through special relativity and the influence of acceleration, shows that time can be bent by velocity and gravitational fields. But the twin paradox is just the tip of the iceberg of time's mysteries. There is another paradox that is even more puzzling, the grandfather paradox. Imagine you travel back in time and prevent your grandfather from meeting your grandmother. That means you would never be born. But if you don't exist, how could you go back to prevent that meeting in the first place? This is not just a question of logic, but also a challenge to the law of causality in the universe. Some scientists believe that the laws of physics do not allow such paradoxes to occur. But is that true? Or is the universe operating under a more complex mechanism than we think? Could the universe be like a self-balancing system, adjusting itself to avoid contradictions? Or perhaps all our actions, including time travel, are already part of a grand plan that the universe set up in advance? Are we just small factors in a perfect structure, where all causal loops are not random, but an integral part? This mystery remains unsolved, but it raises a big question. Are we changing the universe, or simply playing a role in how the universe adjusts itself? Another paradox, the bootstrap paradox. Imagine you travel back in time and give Shakespeare a copy of his famous works. Shakespeare uses this copy to publish them, and over generations they become world literary masterpieces. Then you bring that copy back to give to him. So the question is, who actually wrote those works? This is the bootstrap paradox, a strange loop where information or an object seems to have no origin, but only exists because it is passed back and forth in the timeline. A seemingly simple phenomenon makes us question the true nature of origin and creation. But if that's not enough to confuse you, think about the predestination paradox. Suppose you go back to the past to prevent a terrible disaster. But then, your very action is the cause of that disaster. The more you try to change, the more you seem to be drawn into an inevitable chain of events. This leads to a question. Do we really have free will, or is everything predetermined as part of the universe's immutable plan? Could it be that time is not a flow, but a closed structure, where past, present, and future are intertwined inseparably? Some scientists and philosophers believe that in this universe, everything is pre-written, a great book with every event and action contained within its pages. Could it be that what we call freedom is just an illusion, and the true nature of time still surpasses our imagination? To solve these paradoxes, some scientists have proposed the hypothesis of parallel timelines or alternate universes. According to this scenario, each change in the past creates a new branch of reality. This means you can go back in time, create a new flow without conflicting with the original past or present. These paradoxes are not just scientific puzzles. They are an invitation for us to explore deeper into the nature of time, causality, and free will. Can the past be changed, or are we just following a path that has been predetermined? These questions not only challenge our understanding, but also change our view of the universe and our role in it. Although time travel is still beyond our reach, the paradoxes it evokes force us to rethink how time really works. If one day science proves that time travel is possible, how do you think it will change our lives? Perhaps, somewhere in another timeline, a different version of you is living the life you once dreamed of. If you had the opportunity to break the limits of time, what would you do? Imagine, ponder. This universe is vast, mysterious, and full of wonders waiting to be discovered. Each step of science not only opens up answers, but also leads to new questions. Each question is a ray of light illuminating the future. Thank you for joining us on this exciting journey of exploring time. If you like this content, don't forget to subscribe to the channel so you don't miss the next exciting videos. Leave your thoughts in the comments section. What would you do if you could time travel?